Good morning everyone. Today we would like to present assignment 3 and assignment 4, which is designing the schematic diagram for all DB, SSB, PFC and designing the cable installation design. First of all, let's read the introduction. Distribution box DB are crucial for distributing the power safely throughout the buildings, comprising the main switches, circuit breakers, fuses, bus bar, meters and control devices. Sub-switch port SSB provide the localized power distribution, enhancing the efficiency and safety. Power factor correction PFC using methods like capacitor bank improve the system efficiency by reducing the energy losses. The main switchboard serve as the central hub receiving the power from the utility grid and distributing it to the various sub-switchboard or equipment. Proper design and regular maintenance of this system ensure the safe and efficient power distribution. When selecting the cables, considering the voltage rating, insulation material and sheathing to prevent the hazards and ensure the reliability. These careful design and selection are essential for maintaining the performance and safety of the electrical system within like JKR office and mosque. Next, let's see the objective of the both assignment. In assignment 3, we have come out with the 3 objectives. The first objective is to construct the schematic diagram of electrical switchboard for power socket, lighting and air conditioning with the components labeled correctly. Next is to establish which protection device rating is necessary to prevent the overcurrent in the system. And the last one is to figure out the system's overall power factor correction. In assignment 4, the first objective is to ensure the proper sizing and selection cables based on the voltage rating, current carrying capacity and environmental factors. The second objective is to optimize the energy efficiency and improve the power quality by integrating the power factor correction board. The third one is to implement the appropriate protection measures such as circuit breaker, fuses, surge protectors. And the fourth one is to adhere the relevant standard codes and regulation for the compliant safety. And the last one is to optimize the power control signal distribution for diverse the electrical loads including the lighting, power outlet, HVAC systems and other equipments.
At the ground floor office, the MCCB rating for the lighting dB is 30 ampere, for the power socket dB is 40 ampere and for the aircon socket dB is 80 ampere. The MCCB rating of SSB1 is 150 ampere and for MSB is 400 ampere. The RCCB for both lighting dB and power socket dB is 30 ampere. For the AC socket dB and SSB1, earth leakage relay ELR had been selected. This is because the MCCB rating for the AC socket dB and SSB1 is above 60 ampere, hence RCCB cannot be used. For the MSB, the overcurrent and earth fault relay had been selected because the MCCB rating for MSB is 400 ampere, which is above 250 ampere. As an example, the total connected load is 11.823 kilowatt, which is 20.0071 in ampere. The total connected load in ampere is calculated by using the formula TCL in kilowatt is divided by 400, which is the 3-phase voltage, times the power factor, which is 0.85 times square root of 3. The total connected load with extra 30% is 15.3699 kilowatt, which is 26.1002 in ampere. These values are calculated by using the formula TCL times 1.3. The maximum demand is 9.458 kilowatt, which is 16.061 in ampere. The maximum demand is calculated by using the formula TCL times the diversity factor. The maximum demand with extra 30% is 12.2959 kilowatt and 20.8802 in ampere. These values are calculated by using the formula maximum demand times 1.3. The MCCB rating is chosen from Appendix 3C. The MCCB rating value has to be larger than the maximum demand with extra 30%. Hence, the MCCB rating is 30 ampere. The chosen RCCB is 30 ampere. This value is chosen based on the MCCB rating.
First of all, we made some calculation to identify MCCB and RCCB rating as safety features for DB and SSB. We add extra 30% of capacity for total connected load and maximum demand value by using this formula. TCL 30% equals to 1.3 times by multiplied by TCL in kilowatt. Following with maximum demand 30% equals to 1.3 multiplied by maximum demand in kilowatt. The total connected load value and maximum demand value, we took it from previous assignment, which is assignment 2. Then proceed with calculating MPa values. Once calculated, we decide MCCB and RCCB value based on given datasheet. This table refers to the values of TCL and MD after at 30%. We decide MCCB and RCCB value based on maximum demand 30%, but we need TCL 30% for calculating maximum demand 30%. For DB lighting and DB socket, we choose MCCB 30-60 and RCCB value 30 and 60 ampere. For DB AC and SSB, we choose MCCB value 100 ampere and 200 ampere. And RCCB, we choose ELR as safety features because currently we have 60 ampere of RCCB in market, so it exists. And we choose ELR type for RCCB.
The MOSC electrical system included three main distribution board for lighting, power socket, and air conditioner, each with a specific load and protection. First of all is lighting DB. The initial load capacity is 17.126 kilowatt, 29.0823 ampere, with the extra 30% capacity added for the consistent totaling is 22.264 kilowatt and 37.0870 ampere. The maximum demand is 15.413 kilowatt and 26.1734 ampere. The rising to the 20.037 kV and 34.025 ampere. Under peak conditioner, the dB is protected by a 40 ampere MCCB and a 30 ampere RCCB. Second one is power socket DB. It can handle a load of 25.5 kilowatt and 43.3025 ampere, increasing to 33.150 kilowatt hour, 56.2933 ampere with the extra capacity. The maximum demand is 10.2 kilowatt and 17.3210 ampere, rise to 13.260 kilowatt and 22.517 ampere. This dB is protected by a 30 ampere MCCB and RCCB. The third one is AC power socket dB, designed for a load of 3.357 kilowatt and 5.7007 ampere with the extra capacity up to 4.364 kilowatt and 7.4108 ampere. The maximum demand remains steady at 3.357 kilowatt and 5.7007 ampere. Rise to 4.364 kilowatt and 7.411 ampere. It's also protected by a 30 ampere MCCB and RCCB. Each dB is carefully planned to handle its perfection load and protection peak demand, ensuring efficiency power distribution while maintaining safety throughout appropriate protection device like MCCB and RCCB. This board ensuring efficiency and safe power distribution within the MOSC with the sub-switch port SSP3 considering this load for the easy management and protection.
The sub-switch board SSB3 in the MOSC combines the load from all the three main distribution boards: lighting, power socket and aircon socket. It can handle up to 59.778 kW with extra capacity, drawing a maximum current of 101.5112 ampere. Under a normal condition, it handles 49.983 kW and 78.0855 ampere. For a safety, it is protected by an 80 ampere MCCB and ELR earth leakage relay. In our case, we choose ELR due to the MCCB rating more than 60 TPM. The ELR continuously checks for the leakage current that flow to the earth. If it detects the leakage current exceeding a safe threshold, the ELR swiftly disconnects the power supply. This rapid action prevents the potential electric shock or fire, protecting the both electrical infrastructure and MOSC occupants. These devices ensure that the sub-switch board can safely manage peak the loads, disconnecting if necessary to prevent the damage or hazards due to the overload or electrical fault. Furthermore, let's see the power factor correction. To effectively implement the power factor correction in the mosque and the JKR office of an electrical system, several schematic steps are followed. The first step is find the total required capacitor output. Firstly, the total power requiring correction is determined, which amount to 215.963 kilowatt. This calculation consider of an initial power factor of 0.75 and aims to improve to its target of 0.95 power factor. Through the trigonometric calculation, the reactive power is needed to found, resulting in an initial required capacitor output of 119.5 kVAr. Next step is find the total required capacitor output at the capacitor rated voltage, and the third step is find the total required capacitor output with the reactor. Adjustments are made considering system's rated voltage of 440 volt and frequency of 50 Hz, resulting in an adjusted required capacitor output of 144.595 kVAr. Further adjustments are made to include the reactors for stability, ultimately the setting a practical capacitor output of the target approximately 150 kVAr. The fourth step is find the capacitor size for the first stage, and the fifth step is switching program selection. Capacitors are then sized for each correction stage, with the first stage set at 50 kVAr to ensure the capacitor current remains below 1% of the main switch port MCCB rating of 400 ampere. The selection of a switching program is crucial, with program F is chosen for its efficiency in achieving 165 kVAr with the fewer stages compared to the other option. The step 6 is circuit breaker and contactor rating at each stage. We are following the method 1. Following this, circuit breakers and contactors are rated based on the calculated capacitor current at each stage. For instance, the first stage require breaker at 6 ampere with 55% safety margin, and a contactor rated at 4.83 ampere with a 35% margin to ensure the reliable operation and safety. Step 7 is incoming MCCB for the PFC board. Lastly, for incoming supply, an MCCB rated at 300 ampere is chosen after calculating the total capacitor current of 178.93 ampere, adding a 30% safety margin. This comprehensive approach ensures that the PFC system in the mosque and JKR office effectively improves the power efficiency, reduces the energy losses, and operates safely within the electrical distribution network.
In assignment 4, the size and type of cables that can be installed at the ground floor office had been proposed. From SSB1 to power socket DB, SSB1 to lighting DB, SSB1 to aircon DB, the 4x16 mm square PVC cable in conduit had been proposed to be installed. From MSB to SSB1 and MSB to PFC, the 4x95 mm square XLPE PVC cable in conduit had been proposed to be installed. I will explain on the method that I have used to determine the suitable cable size from SSB1 to lighting DB. Firstly, the cable size is assumed to be 16 mm square. The cable type is PVC type. The total length from SSB1 to the lighting DB is 6 meters. The MCCB rating of SSB1 is 30 ampere. Next, the current carrying capacity is 68 ampere based on the table for D1A. The cable voltage drop VDZ is 2.4 millivolt per ampere per meter based on the table for D1B. The voltage drop is calculated based on the formula VDZ, which is 2.4 times the MCCB rating of SSB1, which is 30 ampere, times the total length from the SSB1 to the lighting DB, which is 6 meters, divided by 1000. The calculated voltage drop is 0.432 volt. The percentage of voltage drop is calculated based on the formula voltage drop divided by 400, which is the three-phase voltage times with 100%. The calculated percentage of voltage drop is 0.11%. Since the voltage drop percentage is less than 2%, hence the selected 16 mm square cable is suitable.
This cable was our choice for SSB2 to DB. For this project, we used 4x16 mm square and 4x6 mm square cable conduit. PVC is a superior electric insulator that lowers the possibility of electrical problem and guarantees the electrical system operates safely. PVC cable also make installation simple because of their flexibility and ease of use. They can be bent around corners and tucked in conduit without causing damage to the installation. They may therefore be easily adjusted to a wide range of installation situations. Additionally, PVC has self-extinguishing qualities and is malfunction and increase installation overall safety. The voltage drop of this cable is very low, which is 1.1 for total of 3 dB, which is lighting, aircon and socket. We decide to use XLPE over PVC cable with 4 times 95 mm square conduit cable from MSB to SSB2. Comparing this cable to other cable, the voltage drop is 1.65% only. Elasticity to wire, which facilitates handling and installation. This is especially useful for conduits where the wire may be bent and tucked through with ease without causing any damage to the installation. Furthermore, both PVC and XLPE's fire retardant qualities enhance safety. When burnt, XLPE produces no harmful emission, and PVC is naturally fire resistant and self-extinguishing, which lowers the possibilities of fire spreading in the event of an electrical malfunction. Furthermore, in comparison to traditional PVC insulation, the improved electrical performance of XLPE insulation offers superior electrical qualities, such as lower dielectric constant and stronger dielectric strength. This leads to conventional PVC insulation. This results in improved overall electrical performance of the cable, making it a superior choice for varying demanding application.
Next is in electrical design for the mosque. Careful attention is given to the cable selection to ensure safety, reliability, and efficiency. The selection process considers variant factors such as total connector load, maximum demand, current requirement, and the physical installation environment. From the DB power socket, lighting, and air conditioner to SSP3 cable within the mosque is 4 times 60 millimeters where PVC cable are using in conduit. These cables are chosen due to their current carry capacitor of 68 ampere, which is comfortable exceed the maximum current demand for each circuit, thus preventing overheat and ensuring long-term reliability. The cable used of PVC insulation providing flexible and resistant to environmental factors, making it suitable for the indoor installation where the cable is protected within the conduit. Additionally, the voltage drop calculate a critical part of selection process, ensuring that voltage drop are kept minimum level with the percentage well within acceptable limits.
Now let's talk about the underground cable. For the main supply to the sub-switch port SSB3, a more robust of 4 times 70 mm square XLPE SWA PVC cable is selected laid underground. This cable type is chosen due to its higher current rating capacity of 251 ampere, necessary to handle a higher demand and ensure the minimal voltage drop over a longer distance of 138.01 meters. XLPE cross-link polyethylene insulation offers a superior thermal properties, mechanical strength, and resistance to the chemical and moisture, making it ideal for the underground installation. The additional SWA steel wire armoring provides the mechanical protection against the physical damage, ensuring the cable integrity and safety in an underground environment. The voltage drop calculation are critical part of the selection process, and excessive voltage drop can lead to inefficient operation and the potential damage to the electrical equipment. For the mosque circuit, the voltage drop percentage are kept very low, with the highest being of 1.66% for the main supply to SSP3. Well, within the acceptable limit, this careful consideration ensure that the electrical system operates efficiently with the minimal energy losses and consistent voltage levels supplied to all connected devices. The selection approximately of rated MCB's miniature circuit breaker and MCCB molded case circuit breaker further ensures that each circuit is adequately protected against the overload and short circuit, enhancing the overall safety and reliability of the electrical installation in the mosque.
In this project, we designed a schematic diagram for electrical distribution board in JKR office and mosque, addressing the challenging like space content, component selection, and ensuring electric safety. Key component of circuit breaker and relay was selected based on their benefits and protection features. Economical consider also features including energy consumption and cost calculation using TNB tariff. Detailed calculation determine the requirement capacity output for power factor correction, ensuring operational efficiency and reducing energy losses. Design and implementation of electrical system for JKR office and mosque follow the matriculation approach aimed to ensuring safety, efficiency, and compliance with industry standard, including the selection of cable and integration of PFC ports. In conclusion, the project highlights the importance of a well-designed schematic diagram for the safe and reliable power distribution. Incorporating energy efficiency measures like PFCs are not only enhance system performance but also reduce environmental impact. Adhering to electrical safety standard and considering culture and environmental factor underscore the project commitment to sustain the engineering practice to comprehension approach from the component selection to economical analysis, efficiency, and compliant electrical system for the JKR office and mosque. Overall, the project's attention to the detail in design and compliance is critical for the creating a safe, efficiency, and compliant electrical system support to operational needs for the both facility while promoting energy efficiency and sustainability.